Chapter 14. Chemical effects of electric current. Conduction through solids. We all know that matter is composed of atoms, and every atom consists of charged particles. There exist two types of charged particles: positively charged particles and negatively charged particles. The flow of negatively charged particles inside a substance constitutes an electric current. In some materials, the electric charges can flow easily through the material, whereas in some materials, charges cannot flow. On the basis of the resistance offered by the materials to the flow of current, they are classified as inductors and insulators. Let us now define conductors and insulators. The materials through which electric charges can flow easily are called conductors. An electric current can easily pass through conductors. All the metals like copper, silver, aluminium, gold, etc. are good conductors of electricity. The materials through which electric charges cannot flow are called insulators. These materials do not allow an electric current to pass through them easily. Wood, rubber, cotton, glass, ebonite, paper, etc. are all examples of insulators. They are called poor or non-conductors of electricity. Let's do a quick check. Conduction through liquids. We have seen that electric current can pass through materials like metals, but what about liquids? Do liquids conduct electricity? Before answering this question, let us first study about tester. A tester is a circuit wherein one terminal of a battery is connected in series with a bulb with the help of a connecting wire, and the other free end of the bulb is connected to another connecting wire. Positive terminal of the battery is connected to another connecting wire. Activity. Let us make our own tester. A simple tester can be made with the help of a battery, a torch bulb, few connecting wires, a switch, and two clips. Connect the switch in series with the battery. Connect the another end of the battery with the bulb through a wire. Now, connect the free end of the bulb to a crocodile clip. Say clip A. The free end of the switch is connected to another crocodile clip. Say clip B. Make sure that each connection is tapped. Connect any good conductor, like an iron bead, between the clips A and B. Now, close the switch and observe what happens. We observe that as soon as the switch is closed, the bulb glows. This is because the iron bead, being a good conductor, conducts electricity. Thus, the circuit gets completed, which causes the bulb to glow. This also ensures that our tester is working properly. Let us now perform an activity to test whether a liquid conducts electricity or not. Take they are approximately 1 centimeter away from each other. Now, place this rubber cord in the beaker. Connect the clips A and B of the tester to the nails fixed on the rubber cord. Pour lemon juice in the beaker. Close the switch. What do you observe? Does the bulb of the tester glow? Yes. What causes the bulb to glow? Well, when the liquid between the two iron beam allows the electric current to pass, the circuit of the tester is complete. The current flows in the circuit and the bulb glows. If the same activity is performed by taking solutions like hydrochloric acid solution, vinegar, the bulb glows. But the intensity with which the bulb glows may not be the same in all the solutions. It will differ in all the cases. We can therefore conclude that some liquids allow electric current to pass through them. The liquid which conduct electricity are called conducting liquids or conducting solutions. When an electric current passes through a conducting liquid, a chemical reaction takes place in the solution. This chemical change which takes place in conducting liquids when passing an electric current through them are called chemical effects of electric current. Before proceeding further, let us now understand some terms related with chemical effects of electric current. Electrolyte. A liquid which can conduct electricity is called an electrolyte. In other words, a conducting solution or liquid is called an electrolyte. An electrolyte contains positively and negatively charged ions. It is the flow of these ions which conducts electricity through an electrolyte. Electrolytes are of two types: strong electrolytes and weak electrolytes. Strong electrolytes contain a large number of free ions in them. Thus, a strong electrolyte is a very good conductor of electricity. Potassium hydroxide solution, common salt solution, nitric acid solution, hydrochloric acid solution, copper sulfate solution are some common examples of strong electrolytes. As the name suggests, a weak electrolyte contains very few free ions in it, which can conduct electricity. Thus, a weak electrolyte is a poor conductor of electricity. Vinegar and lemon juice have lesser number of free ions in them. Thus, the extent to which they conduct electricity is less. Tap water, rainwater, ammonium chloride solution, acetic acid solution are some of the examples of weak electrolytes. Electrode. A solid electrical conductor through which an electric current enters or leaves something like a dry cell is called an electrode. Electrodes are made of metals like zinc, copper, etc. Electrodes can also be made up of non-metals like carbon. Electrodes are found in various forms such as wires, plates, or rods. Electrodes are of two types: anode and cathode. The electrode which is connected to the positive terminal of the battery gets positively charged. This positively charged electrode is called anode, whereas the electrode connected to the negative terminal of the battery gets negatively charged. This negatively charged electrode is called cathode. Electrolytic cell. An arrangement having two electrodes kept in a conducting liquid in a vessel through which electric current is passed is called an electrolytic cell. Electrical conductivity. Electrical conductivity is a measure of the ability of a substance to allow the flow of electric current through it. Metals like silver, copper, aluminium, etc. have high electrical conductivity. This indicates that they are very good conductors of electricity and can be used where high conduction of electricity is required. We have learned to make a tester with the help of a battery, torch bulb, and connecting wires. However, sometimes, even if the solution is conductive, the torch bulb of tester does not glow. Let us find out this reason. Let us now make another tester which can detect the flow of weak current passing through a solution by replacing the torch bulb with an LED. An LED lights up even if a weak electric current flows through it. It consumes very less electrical energy as compared to an incandescent bulb. An LED is attached to two wires called leads. One of them is slightly longer than other. The longer lead is always connected to the positive terminal of the battery, while the shorter lead is always connected to its negative terminal. Let us now connect the LED in the tester. Connect the shorter lead to the negative terminal of the battery and longer lead to one of the clips. The other free end of wire coming from the switch will remain attached to clip B. Our tester is ready. Activity. Let us now use the new tester to test weak electrolytes. Take the same arrangement of beaker and rubber cord with iron needles fixed on it. Join the clips A and B to the iron needles. Pour some amount of tap water in the beaker. Close the switch and observe what happens. You will observe that the LED glows. We know that tap water is a weak conductor of electricity. Then, how does the LED glow? This is because the tap water contains some amount of dissolved salts, which supplies enough current in the circuit for the LED to glow. Activity. We can use another effect, that is the magnetic effect of electric current, to make another kind of tester. Take an empty discarded matchbox. Take out the carbon tray from the inside of the matchbox. Now, place a magnetic needle suspended on a pivot in the matchbox tray. Take a copper wire and wind this wire around the tray such that it forms a coil of wire around the magnetic needle. Let us now replace the LED of the tester with a matchbox tray containing compass needle inside it. Connect one end of the copper wire to the terminal of the battery and keep its other end free. Now, you are left with two free ends of wire, one coming from the matchbox and other from the switch. Join them and close the switch momentarily. What do you observe? You observe that the magnetic needle placed inside the matchbox shows deflection. The deflection of the magnetic needle shows that the tester is ready. Like an LED, magnetic needle shows deflection even if the small amount of current is passed through the circuit. Conduction of electricity through different liquids. We know that not all, but some liquids conduct electricity. Let us perform an activity to classify a few commonly used liquid substances as good or bad conductor of electricity. We use the same arrangement of beaker and rubber cord with two iron nails fixed on it. Take small amounts of lemon juice, vegetable oil, milk, honey, tap water, and seawater in separate beakers. Now, pour some amount of Close the switch and observe the magnetic needle. We observe that magnetic needle deflects when an electric current passes through the circuit. This indicates that lead tubes is a good conductor of electricity. Now, open the switch, remove the tester and the rubber core, empty the beaker and wash it with water. Wipe the inside of the beaker and pour a small amount of vegetable oil in it. Place the rubber core in the beaker. Connect the tester. Now, close the switch. Record your observation. The magnetic needle does not deflect when an electric current passes through the circuit. This indicates that vegetable oil is a poor conductor of electricity. Now, replace the vegetable oil by milk in the beaker. In the case of milk, the magnetic needle does not show any deflection. It remains undeflected. This shows that milk is a poor conductor of electricity. Replace the liquid in the beaker with seawater and observe the deflection. When an electric current passes through the seawater, a deflection in the magnetic needle is observed. This indicates that the seawater is a good conductor of electricity. Now replace the seawater in the beaker with tap water and observe the deflection. When an electric current passes through the tap water, the magnetic needle shows deflection. Thus, tap water is a good conductor of electricity. Now, replace the tap water in the beaker with honey and observe the deflection in the magnetic needle. In the case of honey, the magnetic needle does not show any deflection. Thus, honey is a poor conductor of electricity. It is very important to note that materials are broadly classified into good and poor conductors of electricity, instead of classifying them as conductors and insulators, because under certain conditions, most of the materials conduct electricity. Let us now test the conduction of electricity through distilled water by performing an activity. Take the beaker having rubber core with iron nails fixed on it. Now, pour a small amount of distilled water in it. Connect clips A and B of the tester to the iron nails. Close the switch and observe whether the magnetic needle shows deflection or not. You will observe that the magnetic needle does not show deflection. Now, add a pinch of common salt to the distilled water in the beaker. Let it get dissolved. This forms a salt solution. Now, pass an electric current through the salt solution by closing the switch. You will observe a deflection in the magnetic needle this time. Why distilled water does not show any deflection, but salt water does? Well, distilled water being pure does not contain any dissolved salts. It does not provide any ions that can conduct electricity, and hence it is a poor conductor of electricity. On the other hand, a salt solution provides ions that can conduct electricity, thereby making it a good conductor of electricity. The water of taps, hand pumps, wells, etc. always contains small amounts of various mineral salts naturally present in it. These dissolved salts conduct electricity, thereby making these water samples a good conductor of electricity. That is why one should not touch switches or any electrical equipment with wet hands or throw water on electrical fire. Let us now proceed to find out the other ways to make conducting solutions out of distilled water. Take 3 beakers, label them as A, B and C. Now, pour some distilled water in each beaker. With the help of a dropper, add a few drops of dilute hydrochloric acid in beaker A, few drops of caustic soda in beaker B, and a little sugar in beaker C. Take a tester, dip the free ends of the tester in beaker A, such that they are approximately 1 centimeter away from each other. Note that in this activity, we have used the tester without the clips and rubber cork. This is one of the ways to use the tester. Now, close the switch and check whether the magnetic needle shows any deflection or not. You will observe a deflection in the magnetic needle. Before you test the conductivity of other solution, wash and wipe the ends of the tester as they were in contact with the solution used previously. Now, dip the free ends of the tester in beaker B. Close the switch. What do you observe? You observe a deflection in the magnetic needle of the tester. Now, take out the tester. Wash it. And wipe its ends again. And dip its free ends in the beaker C. Close the switch and record your observation. The magnetic needle does not show deflection. Thus, we can conclude that the addition of an acid or a base to distilled water can make it a good conductor of electricity. Let's do a quick check.